Alright, welcome back. We are now going to talk about how to calculate half-life. So remember, half-life is going to be how much of the element or how many of the atoms are remaining after it goes through basically its period of decay. So you can use this nifty equation every single time to calculate your half-life. So A is usually going to be what we're solving for. Now there are variables that you can do to switch this around, but A is going to be the amount after decay. A sub O, this is your initial amount. So it'll say starting with an amount of this many kilograms or however. Then you will always put half in parentheses, and then you're going to have an exponent of n, which is the number or how many times it's gone through a half-life. So we're going to do an example problem here, and I'll show you how to solve for the amount after decay has occurred. Okay, now I already have it written through here just so that you can see it on the PowerPoints. I don't think I can erase it. Nope. Okay, so it says, and this is actually one of your example problems on page, I think 844, or excuse me, 884. This is on page 884 in your textbook. So if you need something where it's like written out step by step, that's where you should look. So it says carbon-14 emits beta radiation and decays with a half-life of 5,730 years. Assume you start with a mass of 2 times 10 to the negative 12th grams. So that's 0.0000002 grams of carbon-14. Okay, so first thing that we could ask you is, how long does carbon-14 take to go through 3 half-lives? So every single half-life is at 5,730 years. Okay, so one half-life, 5,730 years. So if we have 3 half-lives, we're just going to multiply one half-life by 3, and that'll get you, so in 17,190 years, carbon-14 has gone through 3 half-lives. Okay. All right. So the next question we can ask you is, how many grams of carbon-14 are left after 3 half-lives? All right, so again, we're going to use our equation over here. A equals A sub O, half N. So we know that our initial mass of the carbon-14 was 2 times 10 to the negative 12th power. We're going to multiply that times half, and you should put the parentheses into your calculator and then do like 1 divided by 2. Okay, and then your exponent of 3, so you can do a caret 3. What? Okay, so if you do that, if you take 2 times 10 to the negative 12th, because that's what we started with, that's our initial mass, and then in our parentheses, 1 over 2, or 1 divided by 2, close off the parentheses, and then your little caret 3, exponent of 3, you should get 2.50 times 10 to the negative 13th power grams. Okay, so that's 0.0, or so 0.120,250 grams. Okay, so that's after 3 half-lives, that's how much is left. Now, you, page 884, problem number 9, I do want you guys to, I want you to try to work through this problem together. Again, same thing. You're going to use the equation A equals A sub O half N. Okay, it says manganese 56 is beta emitter with a half-life of 2.6 hours. What is the mass of manganese 56 in a 1 milligram sample of the isotope at the end of 10.4 hours? Okay, so I want you to work together. Check your answers when you're finished. I will put this up on, I will pause the video. I'm going to put the answer up and kind of work through it, and then you can check your answers after that. All right, so working through question number 9, okay, so we have A equals 1.0 milligrams times half to the nth power. Now, we don't necessarily know N just yet, okay, but we can solve for that. So that's what this equation over here is for. We know that one half-life is 2.6 hours, and we've gone through 10.4 hours. If you take 10.4, so this is the total amount, divided by one single half-life, which is 2.6 hours, you should get 4 half-lives. So we can insert that 4 into our nth power. Okay, so you get 1.0 milligrams times half to the 4th power. So after you either plug this into your calculator, so just as is, or if you're struggling with finding out how to put the caret 4 in, you can also do 1.0 times half times half times half times half. Okay, now that's going to become a pain in the butt if, let's say, for example, you have 26 half-lives. Okay, so it is best to figure out how to plug this into your calculator, but if you do need to check your answer, maybe you're just a little unsure still, you can do it this way also. But either way, you should get 0.0625 milligrams. Okay, now I want you to think about this quick write, because, man, this would make an excellent test or quiz question, just saying. Will the mass of a substance ever be 0 after going through decay? Why or why not? So let's say you have a substance, it's gone through 1,000 half-lives. Will it ever be 0? And then why or why not? So take your time. I want you to pause the video, answer the quick write, and then come back to it and we will discuss. Alright, so will the mass of a substance ever be 0 after going through decay? Why or why not? Theoretically, no. Theoretically, you will never get to 0 because you're always taking half of something, which will just make it an even smaller number, but in theory, you will never have 0. Now, you can get to a point where if you have like 0.22 zeros and then a 1, not many scales are going to pick that up. They would just say it's 0. But in theory, because atoms are so little, there will always be something left over. Now, last thing that we're going to talk about is transmutation reactions. Basically what this is when you're taking an atom and you're turning it into something else. It's what we go through when we go through alpha decay and beta decay and electron capture. When we take an element or an atom and we turn it into something else, that's going to be the transmutation. Trans means across, mutate means to change. So this is changing across. We can do this a couple different ways. The radioactive decay, like we talked about. Okay, so our radioactive decay. Or we can do what's called particle bombardment. It's a fun term, particle bombardment. And what that is you take other elements, specifically or particularly, a lot of times they'll use helium. And what they do is they speed it up really fast, and then they slam it into the nucleus of another atom, typically uranium, and then they try to create a new atom. So they're not really creating anything because they're not making it. They're just turning it into something else. So they will use what's called a particle accelerator to do this. Again, they use uranium because uranium on the periodic table is the last kind of stable element. It's the last natural element. Anything after element 92, uranium, is going to be a man-made atom. It's not something that occurs naturally. So what they do is they'll take that uranium, like I said, so I'll kind of skip down here, the Large Hadron Collider. What this is it's this really long tube. Okay. And this tube is 27 kilometers in diameter, and there's lots of little tubes, so it actually looks like a circle. I'll show you a picture on the next slide. And so what they'll do is they will have uranium in the tube, and then they'll use another element, so let's say helium, on this side, and then they give it lots of energy, they speed it up, and then they let it go. And throughout this entire tube, the entire process, it's actually has more, I guess, charges that continue to increase the speed of the atom as it flies towards uranium. And then if they do it right, and if everything basically lines up perfectly, then the helium protons in the nucleus will stick to the nucleus of uranium just for a brief period of time. And how they can see this is created is they actually just look for flashes of light. And then they try to capture it on a camera, and then they go in and they'll use an electron microscope to count how many protons are in the nucleus. So, again, this is called the Large Hadron Collider. It's between France and Switzerland, two of the most peaceful countries in the world, for good reason. And actually what they're working on right now is what's called the God particle, or the Higgs boson particles. And that's they're trying to determine basically what the universe looked like before the Big Bang, or as the Big Bang was happening. So as all of the elements and all of the atoms and all of the universe were being created, what were the conditions like? And so that's what they're working on right now. And so this is what this is what the Large Hadron Collider looks like. Again, they have these super big tubes, and this is just a teeny tiny portion of it, because remember, this whole thing, so if this is the start, the end would be 27 kilometers basically that way, and it actually sits underground, about 100 meters underground, just to keep it protected and keep others protected from it. So, and so actually next class, I think you guys will watch a documentary on the Large Hadron Collider and Higgs boson, and how they're trying to create this God particle, so to speak. So it's kind of cool, nuclear physics. So if any of you are interested in that and you are striving to work with the Large Hadron Collider, only the most elite scientists in the world get to work with that. So it's a really good goal to have. All right, so that concludes our decay and transmutation notes. For your practice, I do want you to work on page 884. That's question 10. So I want you to work on that. And then page 886, questions 11 through 16. If you finish early, you can go ahead and get started on chapter 25.3 over fission and fusion, reading through that and taking a few notes of your own. And then you can also start kind of browsing through chapters 25.4, and that's radiation in your life. Where do you come up with radiation? So if you have any questions, shoot me an email. I'll check it when I can, or you can have Mr. Smith email me or text me. And then happy studying.